So the two things we're going to do today, you have kind of now all the tools to do everything, but I'm not usually at this point 100% convinced that you know why you're doing what you're doing and how it all fits together. It's all just kind of been isolated skills for all the series and the convergence, the divergence, what a Maclaurin polynomial is versus a Taylor series and what it means to have this sort of interval of convergence. So I want to seal the deal in like the first 10 minutes. That's what we're going to do. And then we are going to derive what's called Euler's identity, which is e to the I pi plus 1 equals 0. Some people say it's like the most beautiful, here's what they say about it. It's the most beautiful equation of all times. It's a jewel, the most remarkable formula in mathematics. You take it as you will. It might be, for example, like I was told Mount Rushmore's super cool. Went there with my in-laws and was just kind of like, is that it? I know. It was the same with the Baseball Hall of Fame. My husband dragged me there for my honeymoon. We had to stop. I'm like, oh, it could be cool. No, not really. Just looking at, I mean, you know, Babe Ruth's bat. Okay, so what? So you might need to fake it if you don't find it beautiful and exciting, but I think it's cool because I'm a math nerd. But or like, you know, like people want, you're going to find out. Well, they say it's remarkable that you have two of the naturally occurring constants, e and pi. If phi were in there, man, that'd be awesome, but no phi. You don't know what phi is? That's a whole nother discussion. But there's three naturally occurring constants, e, pi, and phi. So this has e and pi in it. It's got our imaginary number, the square root of -1, and then it's combined with the two nicest whole numbers in the world, and they all fit together. That's bizarre. It's cool. But you guys, is this like the Baseball Hall of Fame for you? You're like, yeah, so what? Oh, it's actually, well, you would have to read more. It's in your notes. I have a little clipping of where it says it's used in string theory, and I don't know. That's what it says. Oh, you guys, you're so silly. Anyway, we're going to take 5 minutes and derive it because we now have the math for where it comes from, which is actually kind of a cool thing. So first, on that blank sheet of paper, we're going to take something that I think want to go to. Let's go to Calc BC, shall we? Is that this one? No, yes. No, it's this one. I'm going to find it. All right, this is what I want you to do. Blank sheet of paper. On it, write. What? Yeah, I need a blank sheet. We'll derive this in a minute. I want you to write y equals ln x. Maybe I'll do it right here anyway. So on your blank sheet of paper, write y equals ln x. It's one we've done before. All right. So I really do want to get a blank sheet of paper, and I'm not quite sure why it's not allowing. So I'm going to go over to my computer. So we did, there we go. Now I'm cooking. Now it's giving me everything I had going today. So here we go. What? You guys? Oh, that's right. I got whoever cooked it, probably Riley, trying to kill me. Who was it? Taylor? All right. I'm waiting for my pen to trigger. It's coming. Come on. Why isn't my marker? I have such important stuff to tell you guys today. It will come. So write Taylor polynomial. All right, here we go. Y equals ln x. Let's begin. So I want to tie in a lot of stuff we've been talking about. Let's go put a graph of that parent function on here. Whoa. All right. We obviously can't center our Taylor polynomial or our series or anything at 0 because it's not in the domain of this function. So we're going to do, remember when you had that example number 4 and I had you watch it and then recreate it? We're going to do that same one. That was centered at 1. And I already had you guys create the Taylor polynomial for it. And I want to discuss that versus the series versus the interval of convergence, all of it with this graph. So the first thing we did is we said, I want you to create an nth degree. I'm going to do it down here so you can see it. An nth degree Taylor polynomial. Understand why I can't call it capital M. Why not? It's not centered at 0. It's not Maclaurin. I could call it P sub n of x. That's common, but I'm going to make it a Taylor polynomial. What am I going to do with that? I am going to use it to approximate the actual natural log function. I'm going to center my polynomial at 1. As I bump up the degree, it fits it better because remember I showed you that video where we're bumping it up degree and it's just trying to fit the curvature. So if I do first degree, that's just our linear approximation from Calc AB, and that's really not very accurate. Going to the second degree helps with the concavity. Third degree, it just keeps bumping it up and fitting it better. Remember how we get that just generically. So you have to have that memorized. But remember, we do f of the center. So just in general, let's put f of x equals even so. So I have this function. It's the natural log function. I'm going to make a polynomial that wraps it. We have the model for the Taylor polynomial. It's f prime of c times x minus c to the first, and I'll just take it out. We know this. I just want to show you how it all fits together because it really does help. Squared over 2 factorial plus, and then it ends. For the Taylor polynomial, n is finite. And you're told to do a 4th degree, do a 5th degree, do a 7th degree, but you stop at the end. So I'm going to go ellipse, 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 and the nth derivative, x minus c to the n over n factorial. So there we go. All right, that is my nth degree Taylor polynomial used to approximate the natural log function. Agreed? It's always an approximation when it's a polynomial because it's finite and n stops. Are we good with that? There's always some error. You'll have 2 ways of finding the error depending on what the polynomial looks like. So let's go create it for the natural log function, but not from scratch because that I already had you do. So ours is going to equal, you might not remember what it was because it was last week, but because it's centered at c and natural log of 1 is 0, f of c was 0, so we didn't have anything there. And then it was x minus 1. To the first over 1. Do you remember what came next? You guys remember? Yes, and there was an alternator. So yeah, you're right. It's x minus 1 squared just over 2. The factorial kind of got killed off in the coefficient when you simplified. And then it went plus x minus 1 cubed over 3. And then it went minus, right? This is my 3rd degree Taylor polynomial. What? Oh, why did I write that? Yeah, thank you. X minus 1. So this would be my 3rd degree Taylor polynomial. Agreed? If I were to stop there and ask you for the error, it will be off. Let me show you. It's off everywhere except where? At the center. The farther out I go, the better it hugs the curve. When I get out a certain way, it actually is horrible. So that's where that interval of convergence comes in when we do a power series. So I'm going to show you on Desmos, because I already loaded it in here, what it actually looks like when you graph it and the natural log function. So in red is my natural log. In blue is my 2nd degree. Notice it's kind of following the concavity of it, but then it goes, the blue goes pretty bad after a while. Agreed? And then I did it to the 3rd degree, so I wrapped this green cubic. You can see that it's exact at the center right here, right? And it's actually off a little bit everywhere else. Agreed? That's called the error. Right here, the distance between the actual amount, that right there we call the error. What else is it called? In a word, it's error. What notation do we give it? Yeah, it's actually the distance between the actual function, which in this case was the natural log, but College Board will sometimes just call it a generic f of x. And they'll ask you, what is absolute value of f of x, right? Minus my, let's do, since I'm doing the blue one, that would be my 2nd degree Taylor polynomial for x. This is code language for find the what? Error. Do you agree with that? All right, it's the gap between it. As I increase n, the error gets less and 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 less. Agreed? So if I were to do this all the way out, which I'm going to actually, I'm going to write it as a power series in a little bit. So I'm going to enter series notation to the 99th, and you'll see what happens. But let's go back so you can see what's going on here. So let's put error right here, right? Oh, dang it. My smartboard's not cooperating a whole lot today, but that's okay. Go ahead and write error under there. And let's remind you how to find it. So error, which again might be listed as the absolute value of the distance between the function itself and your approximation. How do we find the error in this case? Just to how far off I am. How would I figure that out? The first unused term, but that only works because this is a alternating series. When it's not alternating, we have a day on how do you do it then, and it's called Lagrange error bound, and it's similar but different. So that error right there is, if I were going to use my function to actually evaluate if I stay close to the center, you can say if I go to 1.1, you'll notice I'll get like a 0.1 squared and then a 0.1 cubed, and that's going to really start getting small and small and small and small. Agreed? If I used it to do ln 5, that would be 4 squared. What's happening to my error? It's getting larger and larger and larger and larger. So for this function, actually, as I veer from the center, it's getting pretty bad. And that's where that interval of convergence comes in. Like, how far out can I go and have it be good, right? So we'll get that in just a second. So right here, your error, so if I wanted to do ln of 1.1, and if I wanted to figure out what the error is, so I put in a 0.1 right here, 0.1 right here, 0.1 right here. That would be my third degree Taylor approximation for the natural log of 1.1. Do you get the language? And a number would come out, and I don't even care what it is. If I were to ask Kev, well, how far off am I? He would say at most, and what would you go enter on your calculator? 0.1 to the, yes, 0.1 to the 4th divided by 4. Agreed? And if I made this even closer to the center, that error is going to even get smaller and smaller. Agreed? So let's go back on here. That was the Taylor polynomial. They were approximations for what actually happened. And listening really today is, even though we're not even doing anything new, I think it's going to tie a whole bunch of stuff together. So then we said, you can write a power series for some functions. Not all functions have a power series that go with them. Some have them that go with it for a while, but then they're really bad. That's what's going to happen with natural log. It doesn't work for all real numbers. Which 3 worked for all real numbers? We already proved it. We already showed it. It was good to go. Sine x was a perfect wrap, right? As long as I go to infinity, sine x, its polynomial can be used for it. Understand why that's super great. When you get when Calc AB gets a polynomial as their integrand, it's kind of like sweet, right? They're easy to derive, they're easy to integrate, they're easy to work with. So we like it when we can use the polynomial. By the way, I told you that's what's programmed into your calculator for sine and e and cosine. For ln, I'm actually not quite sure how your calculator does natural log. That'd be a good thing to, it doesn't. I wonder if it uses e, but anyway, that's a good question. So, but let's go back up here now and talk about a power series. A power series always has the x in it, and it's used where you set your function equal to some series. We create it. We do the Taylor series. We said x to the n over n factorial is actually e, right, to the x as n goes from, I believe we start that one at 0 and go to infinity, right? Boom. And I can say these are equal. Not only are they equal for some x, they're equal for what? All x. Now watch natural logs, okay? I told you when we put in a 5 in there, that error goes a little bit bananas. That's because 5 is not in its interval of convergence. Does that make sense? So what we'll do is, let's go take that one we created, all right? It's the sum as n goes from, we're going to wait for a second. It had an alternator. I always wait on the alternator's index, so or exponent, so just wait for that. There's always an x minus 1 to the nth over n. Wouldn't you agree? However, my n, if I want to write it like that, remember it started at x minus 1 to the first over 1 and then x minus 1 to set. So my count for this one starts at what? Actually, no, 1. But that means I have to mess with my alternator. Because if I put in a 1, it'd start off as negative, and that one didn't. So that's why sometimes we have to kind of tweak things a little bit once you decide on your count. So if my count starts at 1, what must my alternator start at? You have 2 options. Awesome. N minus 1 or N plus 1. I don't really care. And it doesn't affect our ratio test, but it affects something else. So that's actually super important. Somebody yesterday, I said, it's great except your alternator's off. And I kind of minimized it, but that's a huge issue, like globally. Like that was you, wasn't it, Chucky? All right. So that right there it's going to affect what happens on the ends of our interval of convergence. So let's go talk about that. So the next thing we said is the domain of your power series is the set of all x that make it converge. And we said for E, it's infinite, right? And for sine we proved all that. Let's see this guy. This is natural logs, by the way. I am going to replace natural log of x with this. Where is it good? What's the domain of my power series? Let's go take a look. I'll run my ratio test. I'll take the limit as n approaches infinity. Absolute value bars are absolutely necessary, right? And it would be x minus 1 to the n plus 1 over n plus 1. What happened to my alternator? Gone. Yep, the absolute value kills it, right? Then we multiply it by n over x minus 1 to the n. What do we want to do? We want to see where it does what? Converges. So less than 1, exactly, Luke. But remember why? Because I would really like to know when is my polynomial, right, or my Taylor series equal to the function. And that's what I'm finding. It's not everywhere for this one. So let's go do what we've said we do. We take care of this guy and this guy. It's going to leave an x minus 1 on the top. What did I say you do with everything non-attached to the count? Take it out front. Yep, so I would suggest you make that absolute value of x minus 1. Notice they're very necessary. The limit of the rest of this is just the n over n plus 1. What's that guy's limit? Just because we know. It's 1. You could L'Hopital it, but we know it's 1. It always has been. You don't need to write anything else down for that. So this is what I have. Understand what these guys are called. This is called the center. What's this called? Yes, that's what you put when it asks you for the radius of convergence. It tells you how far from the center they're exactly the same. So it tells me I can move 1 away from where? 1. Exactly, which means if I think it out, it's at 2 and at 0. Okay, so I know most of you solve it like this, and that's fine, but I really want you to think about that. This tells you how far from the center you can move to retain the convergence. Are we good? You guys are nodding and stuff. I'm thinking this is sealing the deal for some of you. So over here, I actually do get between 0 and 2. Then what did we say we have to do? We have to see what happens at the end point. Does it converge at 2 and then go crazy, or does it just, can I not include 2? Same with 0. The 0 one should be obvious to you. What do you think is going to happen? Just based on the function itself and what the parent function looks like. It's going to, yeah, it will, but I still want you to know how to run the test. So right now we're trying to decide if we're, how we bracket that. Wimpy, wimpy, right? My gut tells me divergence at 0, but let's show it. So when you guys say test them, because some people were gone that day, and that's something we need to talk about. What do I mean by test them? Yes, plug them in for x. Send natural log 2 into this function, put it in here, and now we're back to the first part of the chapter. That's why it was so important that you knew how to run all those tests. We're going to take n going from 1 to infinity. The alternator is necessary. We'll do 2 minus 1, which is 1 to the n, which is what, Sydney? It bugs you, but what is it? Yep. So I'm just going to erase this. What are you 100% sure this series does? And why? Because we have to justify our answer. This is a what? This is a, what kind? Convergent or divergent alternating series? Convergent. Why? Yep. Because the limit as n approaches infinity in the absence of the alternator is what? 0. Correct? It's what kind of convergent? Last chapter, what would you have said? It's conditionally convergent, but the condition I need is there. It needs the alternator to converge, and it's there. Agreed? So we will write converges, but that could be a 50-50 guess. By the what? By the alternating series test, exactly. I would suggest, I've never read for BC, only AB, so I would suggest covering your bases on that. I think it's okay just to write converges by the alternating, what? That was for 2, yep, I should have written, right, that, x equals 2. So it converges by the alternating series test. You might want to write limit as n approaches infinity of that rule of sequence is equaling 0 on that decreasing function. So you might want to. I don't think it's necessary, but if it is, cover your base. Right, Eli? All right, next step I would test 0. And I know it's going to diverge. There's a vertical asymptote over there, so, but I want to show you with the series why it does and what falls out. So I'm going to still do this. I'll replace it x with a 0. So remember, if you go back up here, replacing x with the 0 now gives me a -1 to the nth. So I have -1 to the n plus 1, and I have a -1 to the nth. Agreed? All over what? There. The question is, what's happening up on the top? What'd you say? Well, there's a couple ways you can think of it. Yes, you could think of it as -1 to the 2n, which is just 1. And then there'd be a -1 left over. That's one way to think about it. You could make this -1 to the n, right? And then, or -1 to the n, and then it'd be over -1 if you wanted to do that. It really doesn't quite matter, except you have to realize that when it's all said and done, what is the top? It's not going to alternate. What will it be? -1. So it's actually -1, a multiple of, so let's go put that on there. It's actually a -1 over n, as n goes from 1 to infinity. You will say that's diverges. Why? You have to give me more. It is a harmonic. Yeah, it's a multiple of the divergent harmonic. But I think if you just wrote divergent harmonic, you're good. All right? So here's my interval of convergence, 0, 2. That means anything outside of there, my series and my function do not match up, and I can never make increasing n. Not only doesn't make it better, it makes it astronomically what? What do you think? Just watch me go try it up here. If I were to say, increasing x, I'll let x be 10. Let's go way back up to where we wrote it out with the polynomial. God dang, spinning wheel of doom again. So if I go up here and I go outside of my radius of convergence, my error will be what? Even if I just do my finite polynomial, not my infinite series, right? How would I get my error? It'd be 9 to the 4th over 4. And the bigger it gets, it actually starts to go really, really bad. But from 0 to 2, not including 0, it's a perfect fit. So back, we're almost done. So back to the Desmos thing so you can see it happening. I just want you to know what you're finding, because I think you guys are good at doing what you need to do, but I'm not quite sure you're understanding what you're doing. So back to the Desmos. Let's go, and then we'll go prove my beautiful Euler's identity. All right, so back to Desmos. Desmos allows me to enter a series, which is why I'm using this instead of my graphing calculator. It's going to make, I can enter the power series and it'll graph it for me. So if I click on, why won't it? It won't give me my keyboard. Crap. Well, anyway, I'll show you what would happen. I'm having computer issues today, and I think I have too many windows open. So if I were to send this to 99 and enter the sum, let me just do it. If I had done this, and I had entered my alternator, which was n plus 1, and then it was x minus 1 to the nth over nth. If I hit graph, this is what you would see it do. It would be so close to the red one, you wouldn't even know it's different. All the way like this, it would wrap it perfectly, and then at 2, it actually just shoots and goes crazy. So are we good? Do we understand what all that stuff stands for? All right, perfect. You're nodding. I like it. It means I didn't waste my time. So now back to your notes. Go to the page. I have so many windows open. There should be a page in there that's got Bart Simpson. And then it's got our good friend Leonard Euler. Do you guys know what it's coming out of his head? Do you guys speak German? Mein Hut ist hässlich. Yes, Eli, good for you. Means my hat is ugly, and it truly is an ugly hat. Don't you agree? I put that in myself. The rest I took off the internet. Can you tell? Hi. Can you tell I added that? My own drawing. You know what's really funny? The first year I made these notes, I had screenshot these two things separately. And so I went to grab the screenshot to put it in the notes, but I'd also Googled a recipe for lemon pound cake, and I'd screenshot that. And so I dumped in my most recent screenshot, boom, didn't ever look at it, and then I ran off the packet. So they're like, what is with this? I'm like, what? They're like, why is there a recipe for lemon pound cake next to Leonard Euler? I'm like, yeah, it's like, stir the eggs gently, and they're like, what the heck? Anyway, it's kind of funny. I know. It was a funny day. I was like, that wasn't supposed to be there. I know, it left the lemon pound cake. That's funny. I don't care who you are. All right, let's go. First thing I want you to do is write out the power series expansion for e to the x, centered at 0, out to 7, actually. I think I want you to get to the 7th degree, then ellipse it. Give me the nth term and ellipse it. You should know exactly what all that means. I want you to go out to the 7th degree for e, then dot, dot, dot. Give me its nth term, also called the general term. Oh, bless you, sunshine. I'm in a mood today. This is actually really fun for me today, because guess what I had to teach in AB this morning? How to make a slope field. Oh, I know, it's awful. It's so easy and annoying and tedious, and I hate them. And I kind of told them that, so they I didn't say, this is going to be awesome. Awesome. All right, so let's see what you wrote. E to the x, what's its expansion? Go ahead, Eli, read it off. Yes. Yes. He's got it. All right, I'm going to go out to 7. I need this many so you can see patterns that happen. So bear with me as I kind of brute force it here. No alternator for E, correct? Which means how do I find its error if I chop it off here? That's coming. That's it. Next week, I think. Plus x to the 7th over 7 factorial. Let's ellipse. Let's general term it. X to the n over n factorial plus dot, dot, dot. Because this is the series, it's going on out to what? Infinity. I could write it with the summation notation, all that good stuff. Let's tell us where the count starts. This one I would start at 0. Yep. So I would have e to the 0 first. So n greater than or equal to 0, I like that there. Now I'm going to take the x out and replace it with the I pi or pi I, whatever you want. So we're going to do e to the, actually it's usually written as like this, and it's actually called Euler's identity, but e to the I pi plus 1 equals 0 is how it's generally written, but we're going to go replace each of those x's with I pi. So go ahead and do that, I pi, and then we do I pi squared. I'm going to distribute that in, so I'm going to do I squared pi squared with my little I squared. Just kidding. I squared, pi squared. I'm being goofy. I don't care, Danny. You can make fun of me. My hamburger was delicious. I'm not doing slope fields. It's good stuff. Nothing new, so nothing to stress you out. I want you to write them all out because something happens. Pi to the 4th over 4 factorial. I to the fifth pi to the fifth over 5 factorial. Don't show this to anybody in Calc AB. It looks way harder than it actually is. Plus I to the sixth pi to the sixth. You guys do the seventh one if you can fit it. I'm going to just stop because I ran out of real estate up there. Are we good? Next, we have to know what powers of I are. So that kind of sends you back into Algebra 2, but off to the side, we're going to replace I with what it is. Like, what is I to the fifth if you were to simplify it? So what's the definition of the imaginary number? I itself is what? Perfect. So it'll be cyclical in a little bit, so we're only going to list them out until it starts to repeat itself. So I squared, I would just square this and it'd pop the root off. So what's I squared? And that's about as far as you get in Algebra 2. You're either working with I or I squared, but we're going to take it farther. I cubed would be I squared times I. Negative, yep, negative I. We're going to write them in terms of I. All right, I to the fourth would be I squared squared. 1. Yep, I to the fifth would be I times I to the fourth, which is back to being I. So it just went cyclical. So right here, whoops, I grabbed my handprint. Right there, it's going to go, it goes I, negative 1, negative I, 1. So it goes I, negative 1, negative I, 1. It'd keep repeating every 4 powers. So we'll replace all of our powers of I with a simplified version. They'll be replaced with either I, negative 1, 1, or negative I. Agreed? So let's go do that. My 1 is a 1 is a 1 is a 1. My I is as good as it gets, but I will replace the I squared with a what? Negative 1. So I'll have a minus 1, technically, pi squared over 2. Factorial is fine. My I cubed, what am I going to replace it with? Yep, negative I, perfect. We'll do that. My I to the fourth is just 1, so that'll be plus pi to, and we'll take it out to 7, just because you need enough of them. So then it cycles back, and so the next one is just what? I. I pi to the fifth over 5 factorial, so we're at this guy, right? I to the sixth will be a minus 1, so it'll be minus pi to the sixth over 6 factorial. I'm going to do the last one. Pi to the seventh would be a minus I pi to the seventh over 7 factorial, and then I'll just dot on out to the end. Here's what you're going to do. We're going to gather all the terms that don't have the i's in them and write them down. Okay, so we're going to rearrange. Addition's commutative, so we're fine with doing that. We're going to do 1 minus pi squared over 2 factorial. What's the next one that does not have an I in it? And if you tuned out and you're like, I don't care, it's like me at the Baseball Hall of Fame. I get it, but this is actually cool, so I'm doing it. All right, what's the next one I'm going to write down? Yeah, pi to the fourth over 4 factorial. And then I have the minus pi to the sixth over 6 factorial. I'm going to go plus dot, put in its general term. This is actually an alternator, right? It's pi to the 2n over 2n factorial. That takes care of all the non-I stuff. Does that look familiar to you? This could be on the AP exam, by the way. They could say this equals and be multiple choice, and here's the answers. 0, 1, diverges, negative 1, 2. There. What is that up there? It's something you know. It's cosine's expansion, so it's actually cosine x with x being pi. Yeah, what is that? That's negative 1. All the non-i's are going to be a negative 1. All right, so that's a negative 1. That's how the 1 comes into play, right? Then over here, I'm going to factor the I out of all the rest of this stuff. So you'll notice everything with an I in it, I will start writing down. Are you all right with that? It will be pi. Minus pi cubed over 3 factorial. Right? Plus pi to the fifth over 5 factorial, etc., 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 alternator, general term, blah, blah, blah. I don't want to write it down, but you should recognize it. It's I what? Sine pi. Agreed? So that's actually I, here's what I have. It was actually cosine pi plus I sine pi is really what I had. Do you agree with me? What is cosine pi? There it is. What's sine of pi? Okay, that's gone. So here's what I have. E to the I pi actually equals -1. Euler's identity is e to the I pi plus 1 actually equals 0. So it's because of the series expansions that happens. That is cool, shizn' it, y'all? And I didn't swear. Shizn' it's my own made-up word. See? That's cool, right? Or is it like the Grand Canyon for you? Oh, I don't know the answer to that. I have not made it high enough into the depths of the high heights of sciences. I have no clue. But read that little blurb on the bottom. I think it says something. I don't know. I don't use it because it says on here it's used in quantum mechanics in the physics of time. So you figure that out. I don't know. Yeah, there's an equation for time. All right, I'm going to stop this. You guys can take the last 15